go on with this exercise, okay? Now, as I was saying before, okay, there are two ways that we can analyze this. The first thing that you have to be clear is what is the sector that we want to analyze. Let me go back, okay? The first day of class of this chapter, okay? This is what we said, okay? In green, we defined the sector where we want to apply the axial force. Okay, so in this case, there are two options. And we're going to consider both here so you can get convinced. Okay, so this is the first one. Okay, so why don't we define the sector? Okay, this is the complete beam. Okay, so the sector that we are going to be analyzing is this one. If you want, because of symmetry, let's consider that we start here. Let me erase. Please, people, don't write on my screen. Come on. Okay, so this is like a D dot. Okay, this is 5. Okay, so that's the direction where we define the position of the cut. Question: this cut is positive or a negative phase? Positive or negative phase?
Positive phase, because we took in the left direction the S.
No, no. This is the Y. This is the axis that we are considering. From here, we measure up, or we can go in the other direction.
Negative phase.
It's a negative phase because we're going. See, you integrate from here, and you go all the way up to here and up to here. So this is a negative phase. Because you go like this. You start here and end up here and here. So this is a negative phase. Okay? So that's key in these things. Okay? That's key. Now, if this is a negative phase, again, I have to draw now, let me on the left-hand side here, let me recall the equation that we're applying. Okay, so we said tau x s, no, xx, well, it's the same, is equal to v of x divided by I sub c, b of s, and we said that these three things are positive and multiply by Q of S. People, it's very important. Don't get confused. Question for you. In the sector, this is the, I just crossed out the sector, okay? In this figure, in this starting in this cut, this is the sector that we are considering. This is the sector that we are considering. Q of S is positive or negative? Mr. Chin Chin, what do you say? Q of S is positive or negative?
It depends of the centroid, right?
Pardon me?
The value of QS depends of the centroid, right?
Yeah. In this case, the centroid is here.
So it is negative.
It's negative. Mr. Dominguez, Salim Dominguez, do you think it's positive or negative?
Negative.
Negative, two negatives. No, it is positive. It is positive. Let's see just by simple reasoning. Okay, not mathematics, simple reasoning. Consider from this side, from the neutral axis and up. Okay, let's call it Q up. Of course, this is positive. Now, let's consider the lower part is always, well, this is negative because the area is positive, but the Y average is negative because pointing downward. Okay, so right now, we need to know which one is larger in absolute value, this or that. Mr. Soria, which one is larger in absolute value, this or that? Mr. Soria, please.
Q up.
Why? Why? It is correct. It is correct. The upper is larger than the lower in absolute value. But why is that? Check the area. Check the flange. Okay. Here in the up, you have the full flange. And in the lower part, you don't include this in that part. So the area of the flange, which will contribute to the Q lower, is smaller than the flange, the upper flange, because it's a full width, which is included here. So this is going to be larger than that one in absolute value. But this is larger than this one. That means that this is going to be positive. So the stress, shear stress, has to be written in the positive direction. Okay, so finally, this is a negative phase, right? Negative phase. So we point it in that direction. So here, okay, we have to point, that's going to be my tau x s. This is going to be tau s x, this is xs. See, people? Any questions, people, please?
But doctor, if we only consider the lower flange in the other side, it's gonna be the opposite to that direction of the shear stress?
Yeah, yeah, you have to reason. You have to reason, but yeah, you're right. Because in that case, in the cut D plus or D prime on the other side, that's going to be also a negative phase, right? If you make a cut here, that's what you're asked. Oh shit! Yes. I'm sorry. If you make a cut here in D prime, okay, that's going to be a negative phase. So again, T tau Sx will point in the minus X direction, and in that case, the tau Xs will point in this direction. Now, Ms. Santos, did I answer your question? Ms. Santos? I think it was Ms. Santos, right?
Yes, but
Okay. Did I answer your question, your concern?
no, I thought that
You
only I
want to
can
consider this?
yes, just that.
Yeah,
just that.
that's coming. It's coming next. It's coming next. Okay, people. Is there any questions about this? Any questions about this? Okay.
Yes,
No.
doctor. I had the question. Carranza.
Yeah.
In case of the non-symmetrical I-beams, why
Yeah,
the why they change the shear stress?
It's similar because in that case, remember that, see, what happens is this. When you, let me try to draw up here. Right, where is my pointer? Okay, up here. Oh, Jesus Christ. Here, remember, Q is equal to the integral of y dA, okay? And when you integrate over the whole section, what's the value of this? Do you remember that? Do you remember the value? What's the result if you integrate this over the whole section?
The area times y.
No, over the whole section, You integrate over the whole section.
0.
Why is that? Who said 0? It's correct, but why? Do you remember why?
Don't remember, doctor.
But it's 0, yeah, you're right.
Because
But
the
why is
center
0?
is
Because the
0.
origin is, yeah, because the origin we located at the centroid. Yes, that's the reason. Okay, now what we can do is this. Okay, we know that it is 0, right? So what we can do is, here it is. So I can say, okay, so this is positive, this is negative, right? So if you want to, for example, if you want the thickness of the lower flange be larger, right? This neutral axis will be a little bit below, but this is still true, right? So if you do not include part of this, that means that this one here is going to be in absolute value smaller than this one, similar to this case. So if you reduce this a little bit because you are not including the full flange, the lower flange, that means that in absolute value, this is going to be smaller than this one. And when you combine, the combination will be positive. Did I answer your concern when you have no symmetry in the vertical direction?
Yes, doctor, thank you.
No problem. Now, somebody asked if we have to calculate the sector from this cut D and D prime all the way up here, that's a very long process. Why don't we try to take advantage and analyze just this little piece? Somebody suggested that, and yeah, that's very smart. We always should be trying to find ways to calculate things in a more easier way. This is what we're going to, that's what we're going to be doing here. Okay, now, let's consider not the original sector, but the lower part of the sector. So this is now the sector that we are analyzing. So that's my S direction, because I go from here until here, and this is free edge. Question: this is a positive or negative phase?
Positive phase.
It is?
Positive. Positive.
Negative.
Positive phase.
Negative.
Positive.
There's only one chance, people. It's a negative phase, right? Or positive phase.
Negative because
No.
it's
Positive.
It's a negative phase. It's a negative phase. So because the end will point in the opposite than this one here. Okay? Now, let's review our equation. So the equation is for Sx is equal to, what was the equation, people? Remind me. Mr. Guaman, do you remember the equation? Here, Mr. Guaman? Don't give me the name of the variables. Give me the interpretation. What do you have here? Mr. Guaman, come on, don't make me waste time. Miss Poveda, what do we have in the numerator? Miss Poveda,
Yes, doctor.
what do you have here in the numerator? Come on, don't make me waste time. Mr. Vasquez,
It is Ix times Q over IC times B.
yeah, okay, all of this in this case is positive, right? Because the shear force is positive and these two parameters are always positive. Question for you people. This value of Q of S for this case is positive or negative? Don't answer. Let me ask somebody. Mr. Jean-Paul Benavides. In this case, this is the sector that we are analyzing. Is it positive or negative? This is the sector.
Okay.
The Q of S of this sector is positive or negative?
So that is negative
Why is that?
because we want to know that the
No,
direction.
no.
The center of this position is negative.
Just a second, please, let me, everybody has to participate. Please, be patient. Your time will come. Mr. Benavides, you said that Q of S is negative or positive, whatever. Why is that? That's my question.
Because Y average is going downward and it's in the negative.
Exactly. That's the answer. That's the answer. Q of S is equal to, or we can express it as the product of the area of the sector multiplied by the Y average of that sector. Okay, this is always positive. People, don't give me a negative area. There is no negative areas in this world. But from here, we have this is Y, and you can see that this is pointing downward. So this is negative. So this is negative. As a result, tau on this cut is going to be also negative. Okay, now let's point it. Okay, if this is a negative area, you have in that direction, that's the positive. So that means that this is tau S X. Are you with me, people? Please. Are you with me? Are you with me, people? So that's a negative phase. In the negative phase, tau points in the negative X direction. In the negative phase, a negative shear stress points in the positive X direction. Now, if that tau is X, now we can write tau XS, points to the right. And we can see that coincides with this. Questions, people? Questions? No questions? Okay, now we have, let me go back. analyzed for a positive shear force. We have determined the shear stress on the different points of this section, right? And we have seen that here on the flange, on the left side of the flange, it points to the left. On the flange, upper flange, on the right hand side, the shear stress points to the right. Okay, then we make a cut here, and we determine that the shear stress points in the upward direction. Finally, we make a cut in the lower flange, and on the left, it points to the right. Okay, and on the right, it points to the left. And we analyze that, and we check that it is indeed correct. Now, let's summarize all of our results in here. Okay, so we said here to the left, here to the right, here in the upward direction, here to the right. What we can do, we can complete this distribution of tau. Okay, so this is tau xs as function of s. So if we make cut in the lower position in the neutral on the neutral axis, the value of q, large q, is going to be the largest. That means that we're going to have the largest value in here. And then if we make cut here, you can see that the q is going to decrease. Why? Because we're adding material below the neutral axis. And that material will contribute with a negative first moment because the y average will be negative. So we're going to have something like this. They're going to decrease. Okay. Now, if we go cuts in this direction, if we make a cut here, okay, the area will be very small. So that means that this arrow will decrease as we go in this direction. Similarly, in the other direction, here going to be here. Now, if we make a cut here, okay, if we make a cut here, we have this value. If we make a cut here, we have to consider this area and also this area. So we're going to have a jump. So this is going to be much larger than this and that. Okay, now I'm talking about tau. If we consider the value of q, okay, that's the first moment. The value of q for a cut in here will be the summation of the value of q when we make a cut here plus the value of the q when we make a cut here. That's what we call, that's the reason we call it shear flow. In the lower part, we have something similar. This is going to decrease. This is going to be like this, like that. Very small, very small. Okay. Now, there are a couple of things that we have to have in mind. Okay. Have in mind that this distribution of shear stress has to be equivalent, statically equivalent with the shear forces or the internal forces acting on that section. Let me write down here. Okay, so the stress distribution has to be statically equivalent with the internal forces. So right now, we are considering these stresses, okay, that that they are acting in the direction of the cut. Okay, now, this we presume is equivalent to that. Okay, now, that's the only shear force that we're having. Okay, so if we have loading in bi-direction, only shear force B is developed. Cut. What does that mean? That means that if we integrate these stresses, the only net force that we have to obtain is in the y direction, it is V, okay? So in the vertical direction, this is y, and this is the z direction. This. So if we integrate these, the only force that we have to recuperate is this one. Why? Because we are considering only forces in the loading in the y direction. Okay, now we have a problem here because you can see that these forces or these shear stresses multiplied by area will give us a force, okay? Let's call it V sub C. We have problem, no problem. Why? Because you can see on the right-hand side, this will also produce a force in the Z direction, and this will cancel that one. Similarly, in the lower edge, in the lower flange, I'm sorry, we're going to have a force to the right and a force to the left. Again, this will cancel and we're fine. So we have to check, this is something that you have to do in the homework, is that if you consider this part here, okay, that's what we call a vertical element, okay, and that will integrate it, recuperate V. So Jesus, somebody's bugging me. That I don't find who is bugging me, okay? Because that's just too much, people. That's that. So you multiply tau xy, integrated, multiplying by the differential area, so you get a vertical force, elementary vertical force. If you integrate it on the vertical elements, you have to recuperate the shear force, okay? Because remember, shear force is the result of equilibrium. Okay, if that's not true, that means that you are not in equilibrium. Okay, then that's what you have to do in the homework. You have to integrate the shear stress and check that it is indeed corresponds to the shear force. Okay, questions about these, people? Questions? Questions? Okay, now let's I need some space here. Write the expression for the stress here. So it's going to be V of X divided by the inertia times V of S and then Q of S. Okay? And we have to remember that Q of S, we can explain it or we can express it as a product of the area of the sector times the position of the vertical position of the centroid. Okay, so we can go on and see, for example, on a flange. Okay, upper flange. Okay, the Q of S. Okay, if this is S, do you remember the formula for this? Is going to be, the area is going to be B minus S times T times H over 2. Okay, that's the upper flange. You can see immediately that this is a linear variation. Okay. If you put it in the formula for tau, that means that on the upper flange, the shear force, of course, is constant for the whole section. The inertia, again, same thing. And the B in the denominator, usually the thickness is uniform for the flange. So that means that tau will have the same variation as the Q, as the first moment. Since the first moment varies linearly, that means that the tau will vary linearly. Okay. Now, on the right hand on the right hand side part of the flange, of the upper flange, you're going to have the same variation. Okay, I'm not going to write it down. And just to remember, on the web, okay. So on the web, remember, you're going to make a cut here, and this is going to be Y, right? So you have to have the first moment of the full flange, okay? And then you have to add this part here. So it's going to be Q of Y. It's going to be, for the flange, it's going to be 2B T times H over 2, okay? You have to add T of the web. Maybe the T of the web is different than the T of the flange, divided by 2. Then we have H over 2 squared minus Y squared. That's something, that exercise that we made a couple of sessions ago. Questions, people? Questions? Questions? No questions? We can see that in the upper part, the variation is linear. On the web, the variation is quadratic. And the largest value of this Q, of this first moment, will occur when Y is equal to 0. That's on the neutral axis. That's something that we insist, right? In the shear stress distribution, the largest value will appear on the neutral axis, which is the opposite from the normal stress. The normal stress has largest value on the top and on the bottom. And in this case, the shear stress are going to be very small at the top and bottom. Okay. Now, in the next slide, this is something that you have in your class notes. It's a table that I prepared doing different cuts in this section. Unfortunately, I changed the notation. Here I have the cuts. I have 2, 2, 3, 3, 4, 4, and those are different names that the one that we employ. But anyway, that's easy to, you can check. And we have done this integration only, I'm sorry, this distribution only up to the centroid, okay? See that the cut 4 is the last one, is go up to a neutral axis. But we can imagine that from here we have some symmetry downwards, okay? Now, in the fifth column, this is basically the thickness. Okay, so in for each one, these values are calculated or are, I'm sorry, corresponds to the position S. In this case, I measured S from the edge. So we go S from here, and we go up to 7.5. So here, remember that from here to here, that's 15 centimeters. Okay, so if I go up to here, that's half, and that's up to here. So this part here is the flange on one side. Okay, now we keep going with the position S. In this case, we measure S from here downward, but we can convert that into values of Y. Just for plotting, see, you will see that in a minute. I did it like this, okay? And so we go from 0 all the way to 15. Remember that the height of this is 30. Okay, so we have different values along these points up to neutral axis, which is half weight. So that's why we go up to 15, right? Now, with this, we can calculate Q, right? And Q are these formulations here. So for the upper flange, B minus S T times H over 2. And for the web, we have this quadratic variation. But that's the first moment. So we have to evaluate in two parts. Now here, there is a big, let me change color. Okay. This value here, that's equal to B, half of the width times T and H over 2. Okay, that corresponds to half of the flange. Okay. Now, so that's up to here. So we have B, okay, times the thickness, that's the area, and then H over 2. But now you see that there is a large difference. Why? Because immediately, if we make a cut here, we make a cut here, we have to consider the full flange. That means that this 232.5 is twice this value here. Okay, so it's like having a pipe. Okay, you have a pipe going up, and then you bifurcate to the left and to the right. Two piping, the smaller piping goes one to the left and one to the right. How much you go from the left and to the right? Half the punch which was going up in the vertical pipe. See, that's the meaning of this, calling a shear flow. And then we have Q. Again, in the case of the calculation of Q, again, you have that this is half of that. Okay. Well, there is a very small error because this should be 580. It's very close to that. Okay, and this is, remember, this is a shear flow. Okay, so that's what is so interesting, right? Usually, what you will see very often that instead of a shear stress, you plot shear flow. Why? Because it's easier to check. Okay, because you have to satisfy this continuity condition. And then you divide this column, Q, little q, by B to calculate the shear stress. Okay, so you have the distribution, and you see that on the cut 4, you got the largest value, which is 745 kilograms per centimeter square. Okay, and then we said in here that we should recuperate the integrating the shear stress, we should recuperate the shear force, and that's what we are doing here. Okay, we are using only in the vertical element in the web, we're using the first Simpson rule to integrate it. So you said here I have the Simpson factor. Okay, and then we multiply this stress by this, and this is what I obtain. And this is the summation. And here I have to multiply twice because we are considering only the upper part of the web. The increment divided by 3, the increment is 2.5 centimeters times the thickness of the web, and then the summation. And hopefully all of this will give you a value like this, okay? And in this case, you can see this is kilograms force, and the value should be 25,000, okay? And the value that we obtain, since we are, remember that this is the integration is not precise, it's an approximation, it's very close, it's almost 25,000 kilograms, which is 25 tons, okay? Is there any questions about these people? Any questions? Any questions? No questions. A super professor, no questions. That's good or that's bad, right? Usually that's not very good. Okay, right now, I'm going. People, I posted yesterday homework number 2, the assignment number 2. Would you please, everybody, open the assignment number 2 from the Aula Virtual? Everybody, go to Arco Virtual and download your homework, assignment number 2, please, everybody. Mr. Carranza, you have it? Do you have the homework, the assignment number 2?
Yes, doctor, I read yesterday. I see the problem. I resolved it. In this week, I resolved the assignment 2.
Okay, now, would you please read the question, the 0 question, please?
Yes.
Read it now for everybody, please.
Okay. Mechanical properties of the structural steel or metal use are very useful to remember, especially especially if you are analyzing a sheet structure.
Okay,
so
just a second. This is something which is very important, okay? many occasions, okay, you listen to a presentation, a conference, right? And they present a lot of values, for example, using finite elements. You'll see that's a lot of numbers, right? And they look nice, nice colors and combinations, all of that. And immediately try to check, okay? And how can you check? Well, these values of the mechanical properties of the steel are very useful, right? So if they're talking about stresses in a steel structure, immediately you can check, for example, the values of the maximum stress with this value, with the yield point. But that's why you need to have those in your memory, okay? Please, I am not going to tell you the mechanical properties of the steel in an evaluation. You have to learn it. You keep it in your memory. It is being recorded. You are responsible for remembering these values of the steel. It's extremely, extremely useful. Go on, Mr. Carranza.
Okay.
So
you are responsible for remembering the basic properties of the normal steel or marine use.
So that's the Young
Young
modulus.
modulus equal 2.07811 Newton over meter square. And
Yield stress.
yield stress 2055.
No, 2000. 235.
235 Newton over millimeter square. Poisson ratio. Poisson ratio.
Poisson ratio.
Poisson ratio B equal 0.13.
No,
And then
0.3. That's the letter nu. That's nu in. Go on.
and density rho equal 7,008 kilogram over meter cube.
Cubic meter.
Cubic meter.
Okay, so those numbers, okay, you have to remember for the evaluations. So please keep it in your mind. Okay, now about the density, okay, please be careful because when you apply the weight, you don't apply density, you consider a specific weight. So you have to multiply that by 9.8 and you will get newtons per millimeter per cubic meter, okay? In case you need to include the weight of a beam or something, right, of the structure. But that's the density. Okay, now, let's keep closing. Mr. Benavides, would you please keep reading the second paragraph of problem 0?
Okay. For the shear allowable stress of the structural steel, review in the rulers and standards of classification society, det Norsk Veritas. Rules for classification, general, part 3, chapter 5, whole girder strength. You have to report.
Just a second. One of these comments that we received from the industry council was that we need you to be able to get more familiar with in general regulations, okay? That's why I'm asking you to go on and start just having a general idea of the rules from this classification society. Okay, so the name of the classification society is that det Norske Veritas. Okay, so you go in the web, plug that, and there's a lot of information. That's what I was trying to guide you, give you some guidance. Okay, of course, we are interested in ships. So this is a maritime area. So you go to maritime and ships and all of that. And then in the rules for classification in general, okay? Because you will see that there are many rules, believe me. So I just want you to take a look at the general, which is at the very top. And then in there, check out the part 3, okay? And then in part 3, go to chapter 5, which deals with whole girder strength, okay? We will study this in chapter 5, okay? In chapter 5, we will take the whole and we will think that since it's very long compared to the beam or the depth, we consider that as a beam. That's why they call it girder, whole girder, okay? That's the reason. So in there, try to see what is the value of the shear stress, okay? Now, the value of the normal stress that we usually take as our limit is 235. But the value of the shear stress, shear, please be careful, shear stress, we cannot exceed. That's the value that I want you to look it up, okay? If you want to keep it in your memory, better, because that's a number that can be useful. But please don't get confused, okay? In one case, you get a specimen like this and you pull it till it breaks. When you enter the plastic region, that value more or less is 235. This is different, okay? You take a piece like this and you pull it in different directions. So you apply a shear and eventually something similarly happens and finally breaks. How much is the stress to enter in the plastic region? More or less, that's the value that we have to have in shear. Please don't get confused. Okay, Ms. Valdez, do you have problem 1?
Okay. Integrate the shear stress distribution to obtain net force in first section beam dimensions X, B, X, T, and comment on the result.
Solved. Please, when you see, if you try to improve yourself, look at the pronunciation of the last letter. Okay, it's very important because it makes a big difference. Okay, you said net force. No, it's net forces and things like that. So please try to improve yourself. Okay, now what I want you to do is take an I-beam, as we did in the example, but I'm not going to give you any value of shear force, any value of the dimensions, just height, width, and the thickness. Consider that the thickness is uniform. Integrate the shear stresses only in the web. What is the result that you were expecting? What's the result that you are expecting after integrating that? What's the result that you should obtain?
The shear force.
Exactly, the shear force. It's interesting, so you will get it, okay? It's just calculus 1, but you have to include the adequate expressions for all the terminology that we have here, okay? So that's so you can start doing that right away, okay? Let's go on. Mr. Luis Paredes, are you there, Mr. Luis Paredes? Mr. Luis Paredes, are you there? No. Mr. Daniel Paredes, are you there?
Yes, doctor.
Can you read problem 2?
Of course. A steel welded box girder having the dimensions shown in the figure has to transmit a vertical shear force B equal to 360 kpounds
So
Determine
that's 360,000 pounds.
okay.
How do you
Sorry.
transform that into kilograms, Mr. Paredes? How do you transfer pounds into kilograms?
Multiply by 2.2.
No, multiply.
Oh, divide.
How do you transform kilograms into newtons?
Multiply by 9.8.
Good, good. That's what you need to do in order if you want to go into the international system of units. Okay, let's go with somebody else. Let me see. Let me ask somebody. Mr. Hidrobo, could you please go on with reading the problem? Problem 2 we are reading.
Determine the shearing stresses at sections A, B, and C. Check that the sectional inertia is 45,000 inches to the
The
fourth,
fourth,
and the value of the radius
gyration radius. Okay, now, so I don't want, see, I'm giving you that the inertia is that value, but you have to check it. So you have to calculate that and check that you are close to that value, okay? And after that, you have to calculate the radius of gyration, okay? Please, you have the dimension of this section. The radius of gyration that you obtain has to make sense, okay? Physically, you see that it's 100 inches. This, right? So 100 inches is about how much in meters? Miss Avilés, how many meters? It's this wide. It's 100 inches. How many centimeters is that?
I think that is I'm sorry.
No problem.
2.54.
Yeah. Okay. So that's 254 meters, right? So it's about this wide, maybe a little bit more. So the radius and height is about 45 inches. So it's maybe about 1 meter height. So the radius of gyration has to make sense with those dimensions. Okay? Okay, we go. See you Thursday. Please, I'm trying to let you start working with the assignment. Please remember, next Thursday, you have to come to the university and we're going to have the first evaluation. That's going to be in person. Okay? That's going to cover homeworks 1 and 2. So please start working right away. Okay, is there no more questions? Please remember that the class notes are there, and if you need them, yes, you can come and pick them up. $5. Okay, bye-bye now.
Thank you, Dr. Papa.
Thank you, doctor.
Thank you, everyone, Doctor.
Oh, it's no.